What's up guys, and welcome to this video on question 3 of the 2017 final exam. We're going to go over this question which deals with kinematics. Okay, so question 3.1 I will do above. Okay, so 3.1. Okay, so a child is holding a red ball and a blue ball over the edge of a roof. The child throws the red ball vertically upwards in the air and at the same moment drops the blue ball over the edge. On the same set of axes, sketch the velocity time graph for both balls. Label the two balls and choose upwards as positive. Okay, so let's start off with a sketch. Okay, so we have our velocity in meters per second and our time in seconds. Okay, so let's think of what the scenario is, or what's happening here. Okay, so we know there is a child on top of a building, or on top of a roof or something. Okay, and we know that he throws the red ball vertically upwards. Okay, so let's say this child has long arms. He throws one ball vertically upwards, and the other ball he drops. Okay, so the blue ball he drops, and the red ball he throws vertically upwards. Okay, so the first thing we need to know is where do we even start these graphs? Okay, so we know that we've chosen upwards as being positive. So that was given in the question. Okay, so we know he throws the red ball vertically upwards, so we know V initial for the red is positive. But for the blue, remember he's dropping it. If he's dropping something, that means the V initial for the blue is equal to 0. So the initial velocity for the blue is going to start right there at the origin, and the initial velocity for the red is going to start somewhere above the origin in the positive domain. It doesn't matter where, you could put it there, you could put it there, it does not matter where, as long as it is above the axes. Okay, then the next thing we need to know is what are these graphs going to look like? Okay, are they going to be straight line graphs, or are they going to go upwards, downwards? Okay, but we know that this question is essentially a free fall question. Both balls are in free fall. Once they've left the hand of the person standing on the roof, they are in free fall. Okay, and when something is in free fall, we know that the acceleration is equal to gravity, and we know that we took positive as being upwards, so the acceleration will be negative because gravity acts downwards. Okay, knowing this, we know that we're going to have a negative gradient, and we also know that both gradients, so the gradient for the red graph and the blue graph, are going to be the same, and that's because the acceleration is equal to gravity. So what we have is we're going to end up with straight line graphs that are parallel to each other. Okay, and obviously in the question I use different colors, but you're supposed to label one of them, this one being the red graph and this one being the blue graph. Okay, and you get 3 marks for that. Okay, it might have taken me a bit longer because I was explaining that question quite in detail. Okay, cool stuff. On to question 3.2. Okay, so question 3.2 says a cat is 6 meters from a mouse and walking slowly. Okay, and we've been given the velocity of the cat initial is equal to 0.25 meters per second. The cat hunts the mouse for 10 seconds in 2 stages. For the first 8 seconds, okay, so I'm going to write here that 0 to 8, because it's happening in 2 seconds, 2 stages, so 0 to 8, and we have from 8 to 10. Okay, so from 0 to 10, I'm going to say it's a constant. So this is stuff I'm just jotting down as I'm reading. Constant 0.25 meters per second, and for the last 2 seconds, he runs at a constant, again, but faster. Okay, the mouse did not see the cat coming and sat still. So the velocity of the mouse is equal to 0 always, because he is sat still. Okay, cool stuff. So getting into the question, and this is obviously for the cat. Okay, so question 3.2.1. says calculate how far the cat is from the mouse after 8 seconds. Okay, so for a constant velocity, we can use UVAT. So we can use the equation. Let's see what's a nice. So let's write down our UVATs, I guess. UVATS. So is our initial. Okay, so our initial is 0.25. Our final is also 0.25. This is actually a constant velocity question, but it's fine. Our acceleration is an unknown. The time is an unknown, and the distance, the time is known. Time is 8, and the distance is an unknown, and is what we're looking for. So we can, let's see, go to the formula sheet, and if we look at an equation, we can use the 1, 2, 3, 4th equation, or the bottom right equation, which is S equals ut plus a half at squared. So if we use that equation, we can say S is equal to ut plus a half at squared. Okay, and we know that u is 0.25, t is equal to 8, and the acceleration, because it's constant velocity, acceleration is equal to 0, so that term goes to 0. And so what we're left with is that S equals 2 meters. Okay, so that's the distance that the cat covers in the first 8 seconds. So for the 8 seconds, we get to 2 meters. So it says calculate how far the cat is from the mouse. So the distance from the cat to the mouse, is going to be the 6 meters minus 2 meters, which is equal to 4 meters. Okay, from mouse. Okay, otherwise, literally the same process, but we could have used the equation because we have a constant velocity question. We could have used the equation speed equals distance over time, and we know the speed of 0.25. Distance is unknown, and the time is 8 seconds. And so the only unknown here is our distance. So we get d equals 0.25 times 8, which is exactly as that. So we get a distance of 2 meters. Okay, 2 processes, same answer. You can decide which one is easier. Okay, so question 3.2.2. Okay, so question 3.2.2 says draw a position time graph for the cat for the 10 seconds, basically. Relevant values of position and time must be shown on the axes. Consider the mouse's position as position 0. So the mouse is at position 0. Okay, so let's start off with a nice set of axes, and we're drawing a position in meters versus time in seconds graph. Okay, so basically we know 0 is where the mouse is at. Okay, so we know at 10 seconds the cat gets to the mouse. So we know that somewhere here at 10 seconds this graph needs to have the axes. We also know that his position initially is 6 meters from the mouse. Okay, then we also know that after 8 seconds, so after 8 seconds, let's say that's somewhere here, after 8 seconds he has a position of 4 meters. So we have that situation right there, and we know that both stage 1 and stage 2 is a constant velocity. So for a constant velocity, we will have a constant gradient. Okay, so basically all we need to do is connect these points. Okay, like that. So this would be stage 1 with velocity 1, and this would be stage 2 where the gradient is velocity 2. Okay, and we also know that this was 10 seconds. Okay, so I think all the relevant points have been plotted. Yeah. yeah, I think everything's there. Okay, cool stuff. So now we can say for question 3.2.3, calculate how fast the cat runs for the last 2 seconds. Okay, so for the last 2 seconds, how fast is he running? I'm just going to use the simplest method, which is speed equals distance over time, considering that we know it is a constant velocity question. The speed is what we're looking for. We know the distance is he needed to cover 4 meters, okay, and he needs to cover it in 2 seconds. Okay, so S is the only unknown, so S equals 2 meters per second. Okay, so I hope you guys followed that basically, or we could have calculated the gradient for stage 2, which is exactly what we did, or we'll get the same answer if we did that. Okay, cool stuff. And we get 2 marks for that. All those questions are complete. Okay, question 3.3. Okay, so it says a model rocket is fired vertically upwards from rest at ground level. The rocket accelerates, so we know the acceleration equals 20 meters per second squared for 15 seconds, and then runs out of fuel. So after 15 seconds, it is in free fall, and the acceleration is equal to gravity after 15 seconds. Okay, so question 1, or 3.3.1 says calculate the rocket's maximum height above the ground. Okay, so how are we going to do this? We have to do this in 2 stages. Okay, so let's start off by actually drawing out the scenario. Okay, so we know that it starts at the ground, it's fired vertically upwards, then at 15 seconds, and this period, the acceleration equals 20 meters per second upwards. At 15 seconds, it runs out of fuel and will go straight back to the ground. Okay, so what I'm concerned with is the maximum height, which would be somewhere here. So I'm going to label this stage 1, or point 1, and point 2. Or actually, I'm going to name 3 points because the acceleration here is equal to minus 9,8 because it's gravity. So we have 1, 2, and point 3. So we're going to have to do this question in 2 different points. So question 3.3.1, and it's 6 marks, worth 6 marks, so it's understandable. Okay, so we're going to do UVAT for stage 1. UVATS for stage 1. Okay, so the initial velocity, it is fired from rest, so it has an initial velocity of 0. The final velocity is unknown. The acceleration for stage 1 is equal to 20 meters per second, and I'm going to take upwards as being the positive direction. The time we know is 15 seconds, and S is what we're looking for, is the unknown. So we can use the equation, let's say S is equal to UT plus a half AT squared. So we know that U was equal to 0, so this term goes to 0. So we're left with a half times the acceleration, which was 20, times 15 squared is equal to our S. So S is equal to 2,250 meters. Okay, so that I would say is S1. So that's all the way until that point right there. S1. Okay, and I'm also going to calculate the velocity, the final velocity, or the velocity here, the velocity there, which would, using the equation V equals U plus AT. Again, U is equal to 0, so we get the equation A, which is 20, times T, which is 15. So we get a velocity which is equal to 300 meters per second. Okay, and that is upwards again. Okay, so after I've done that, I did that because it's quite easy calculation and it might be useful for the next part of the question. So for stage 2, now I'm going to do UVATs once again. UV, let's give myself some space. UVATS. Okay, so the initial here is going to be the final from the previous stage. So that's, and I'm going to take upwards as being positive once again. So we have 300. The final is going to be 0 because at the top the velocity must be 0 for it to be at its maximum. The acceleration is minus 9,8. The time is an unknown, and s is what we're looking for, which is also an unknown. And this time I'm going to use the equation v squared equals u squared plus 2as. Okay, so what we have is 0 squared is equal to 300 squared plus 2 times minus 9,8 times s. The only unknown in this equation is s, so we can solve for s, which is equal to 4,591,84 meters. Okay, so the maximum height, S max, is going to be equal to, I'm going to label that S2, so S2 would be this distance right here, S2, so S max is equal to S1 plus S2, which is equal to, S1 was 2,250 plus 4,591,84, so S max is equal to 6,841,84 meters. Okay, so that would be our maximum height, and we get ourselves 6 marks for that question. Okay, quite a long question, but if you break it down, it's not too difficult. Also, there are other ways we could have calculated this, potentially using different methods, but this is the method that I thought would be the quickest and easiest. Okay, so question 3.3.2. Calculate the time the rocket is in the air from launch to crashing on the ground. Okay, so from launch, okay, so let me clean this up a little bit. I'm going to try to use the same diagram. Okay, so what we want is the time. So time is the unknown here. So let's do question 3.2 right here. So the unknown is time. So what I'm going to do again is I'm going to resolve this into 2 different sections. So from 1 to 2, which is going to be going, or let's actually leave it how it was. This was 2 and this was 3. So I'm going to go from 1 to 3, okay, because that is the point from the ground where the velocity initial is equal to 0 to the velocity final is equal to 0 as well, and it's at S max, and then from 3 to the ground again, which is at 4. So, and then I'm going to do 3, 2, 4. Okay, so hopefully that will work for us. Okay, so let's get our UVATs, UVATS. Okay, so at the ground, the initial velocity was equal to, let's see, oh, actually, sorry, I've made a mistake here, because I'm going to actually go from 2 to 3, and the reason why I'm going from 2 to 3 is because we know that it takes it 15 seconds to get to 2. So I'm going from 2 to 3, okay, and then from 3 to 4, because I already know 1 to 2 is 15 seconds. Okay, so if I take 1 to 2, we already know that the time is equal to 15 seconds. So we want to work out 2 to 3 and then 3 to 4. Okay, so the initial velocity there was what we calculated as 300. Okay, okay, so we're actually using the same UVAT, so 0 minus 9,8. The time was unknown, and the S we've actually calculated. The S would be equal to, that was S2, which was actually not needed, so I'm just going to leave it. So what I'm looking for is time. So I'm going to use the equation V is equal to U plus AT, and I'm going to take upwards as positive, obviously, because we've taken 300 as positive and minus 9.8 as our gravitational constant. So what we have is V, which is 0, is equal to 300 plus our acceleration, which is minus 9,8, times the time. I'm going to label this t1 is equal to 15 and t2. So as we can see here, t2 is the only unknown. So t2 we can calculate as being equal to 30,61 seconds. Okay, now I'm going to do the UVATs for 3 to 4. So UVATS. Okay, so the initial velocity at 3 is going to be equal to 0. Okay. The final is an unknown. The acceleration we know is still minus 9,8. And we know the time is unknown, but we know the distance. Again, I'm taking upwards as being positive. So the distance it travels, or the displacement it travels from 3 to 4 is downwards. So it is going to be the distance, the maximum distance, S max. But it's going to be a negative because it's downwards, so minus, we calculated it as being 6,841,84 meters. And I'm going to use the equation S is equal to UT plus a half AT squared. Okay, yeah, and the initial here was 0, so that goes to 0. So we have S is equal to a half times minus 9,8. Okay, S we also know is minus 6,841,84 is equal to a half times acceleration times t squared. I'm going to label that t3. The only unknown here is t3, so we can calculate t3 is equal to, and if we calculate it, we get 37,37 seconds. So now what we wanted from this question was the total time from launch to it hitting the ground. So T total is equal to T1 plus T2 plus T3. And if you pull the various values, T1, which was 15, plus T2 plus T3, we get a T total of 82,98 seconds. Okay, that's our final answer. An alternative method, which may actually have been easier, is to actually go from 2 to 3, I mean 2 to 4, straight to 4. And the reason we could have used that is because the acceleration here is always equal to gravity throughout this entire motion. From all the way from 2 all the way till it hits the ground, it's always gravity, so we could have just used that, and we may have actually saved ourselves a little bit of time because we would have only had to go through one UVAT. Okay, so the last question, 3.3.3, at which position will the rocket experience a maximum velocity? So basically we've got 4 options from what we've picked up. We've got either at 1, 2, 3, or 4. Okay, so at 1 and 3, the velocities are equal to 0, so we can actually completely disregard those. So basically, we need to know if it's at 2 or 4. We can do some calculations, but it actually turns out that the maximum velocity would be as it's hitting the ground, because it's accelerated all the way from the top to the bottom. So at position 4, or we can say question 3.3.3, I'll just say it above it, the maximum velocity is as it hits the ground. Okay, and what we get is 2 marks there. We got 5 marks for the previous question, and we end up with 24 marks. Okay, and I think this video was actually longer than the normal video, so you can see it's quite an intense question. But everything's manageable if you break it down into small steps. And yeah, so thanks for watching, guys, and I hope you guys found this useful.